We last left discussing the normalized reflectance from our fiber simulation, and we said that the reflectance goes all the way to 0 when the nanoparticles get to a certain coverage. But in reality, this experiment indicates that these do not get to 0. So what could be the explanation? Well, if I bring your attention back to the model for this system, we modeled it as a layer of glass butt up against a layer of gold in water. Now, the reflectance of 0 means that all of the light coming in is interacting with the gold and none of it is coming back. At least none of it in wavelengths under 500 nanometers. That means all of that light is being absorbed. But in reality, the gold isn't flush up against the glass, at least not in our system. It's tethered to the glass through an intermediate linking layer. This linker is called an organosilane. It binds covalently to glass on one end and covalently, or at least very electrostatically, to gold on the other. This induces a spacer. Now, in this interface, a certain amount of reflectance will always travel backwards because not all of the light will transmit into this third layer. Some of it will reflect off the first layer or off the first interface, and therefore it can never get to the gold. And thus, we hypothesize that there's always going to be a minimum reflectance from this system that should be tuned to the parameters of this film. So the thicker this film, the more reflectance, that baseline that comes back, no matter what the coverage of gold is. Okay, so to test this hypothesis, we come back to our simulation, or our PAME configuration, which I haven't changed since I ran the simulation, and we're going to add a basic layer. This basic layer we're going to represent as organosilanes. We didn't know the dispersion of organosilanes, but we did find some indications that it might be fittable with a cell mirror model, and the parameters that we're using I'm just going to repeat. So we start with our cell mirror model. The size of the silanes from the manufacturer indicates they're about 2 nanometers in thickness. Of course, this is going to vary a little bit. And the dispersion for these we found is best fit when we have the following coefficients: 6.9, 3.2. This one, just leave it as it is. B1 is 1.6. B2 is 0. And B3 is 50. Now we would need to do some sort of an ellipsometric measurement to really get a better idea of the thickness and profile of this film. But with these parameters, we're able to reproduce the correct reflectance profile from the self-assembled monolayer on the fiber that we're measuring in the lab. So I'm using kind of an implicit fit where this is going to give me the reflectance that best represents the fiber. And this is fairly reasonable compared to some other values we found for similar molecules and for the thickness of 2 nanometers. Okay. Now all I have to do is repeat the simulation. Let's call this Wolfrac silanes, and I'll change the description. Just add the note that this is with silanes. Let's select the nanosphere with shell layer again. Come back to simulations, leave all the parameters the same, and again simulate over selected material .vfrac. Let's go ahead and start that, and it's just going to rerun the simulation. Once this is done, all we have to do is go back to our IPython notebook and change the path to this for the file path from our old simulation to this simulation, and the whole notebook can be rerun intact, and we can see the effect that the silanes have on the overall reflectance as a function of nanoparticle coverage. This is about done, and it's going to save to filfrac_silanes.mpickle. So I go back to my notebook. I change this to the new simulation, and I just run all. And by the way, all of this is just some custom matplotlib code for changing the style of the plots. So we'll go ahead and run all below. Everything gets regenerated. And here's the critical difference. Notice that there's now dispersion here, and this signal almost looks like it's been tilted relative to the last one, like it's a bit askew. When you normalize it now, you get a profile that looks like this. And notice that this doesn't go to 0 anymore. In fact, it gets very close to 0. And we've been able to show that this is almost identical, I mean really close to identical as what you see in the experiments, or at least in the self-assembly process of gold nanoparticles on an optical fiber. And so this is confirmation that all of these approximations in the PAME modeling, at least for gold nanoparticles, seem to be okay. Alright, well thank you for your attention, and I hope that you're able to get something out of this program. If you need help, you can contact me directly at hughesadam87@gmail.com, or you can contact the PAME mailing list at if you follow the reference at the documents. Thanks.